Hi, everybody. Well, today we're going to tackle one of the more interesting engineering problems in making the computer that's sitting in front of you. And that's the problem of engineering the memory system. So let me see if I can sort of set up what the engineering problem is we're going to work on here, both this lecture and for the following lecture. So we use a memory system, and we use memories in a couple different places in our block diagram. Here we're showing the main memory on this slide here, where we actually, it's a two-port main memory. We use one of the ports to send over the program counter and get back an instruction, and the other port we use when we're servicing load and store instructions, where we compute a memory address by adding the contents of register A to an offset, and then we send that off to the memory system and get back a piece of data, or in the case of a store we also send over the data. And so one of the two memories that we have in our system is this main memory, and it's basically organized as a billion 32-bit words. So 2 to the 30th words by 32 bits, and it's basically a two-port memory, and then there's also sort of the read and write that happens. Okay, so that's one of our memory systems. The other memory system is the one that is the register file that's built into the CPU data path. That's where we get the two register operands for each instruction, and it has sort of the same organization. It has two read ports and one write port, and it's organized as 32 locations, or 2 to the 5th locations by 32 bits. And they very much work the same in the sense that the reads are combinational and the writes are, I haven't turned on the microphone. They very much work the same. Wow, the voice of God, okay. Thank you. They very much work the same because the reads are combinational and the writes are relative to a clock edge. We have a bunch of technologies available to us, and they sort of vary according to the capacity of the memory that we can build and the latency involved. So the register files that we're dealing with, the latency is measured in tens of picoseconds. They're very expensive to build. That speed is because we're devoting a fair amount of silicon area to getting that. And the fact that they're small also allows them to be fast because the capacitances involved in the signaling wires are small because they don't have to go very far. At the other end of the spectrum, we go through both static RAMs and DRAMs. I'll say a little bit about the technologies of those in the next couple slides. And as we go up the hierarchy in terms of capacity, we're also going up the hierarchy in terms of latency. And the main memory that we're talking about is built out of this dynamic RAM technology, and I'll explain why it's called dynamic in just a second. And we can get hundreds of megabytes is slightly obsolete. Now we're in the handful of gigabytes range, so 4 gigabytes or 8 gigabytes, something like that is what most of us have. The trouble is the latency is long compared to the length of an instruction. So an instruction might be executing in a nanosecond or so, or half a nanosecond, and yet the cost of going out to memory to fetch a piece of information is on the order of 40 nanoseconds, so 10 times as long, or something on that thing. And you look at that and you sort of go, wait a minute, there's a problem here, Chris. If I have to fetch each instruction from memory, how does that work? How is it I'm able to execute instructions in 1 nanosecond, but part of executing each instruction is fetching it from memory, and that takes 40 nanoseconds. That just seems like a real fly in the ointment, and indeed it is. And in fact, over the last 3 or 4 decades, what's happened is that the speed of our logic has increased as the CMOS technology has improved, and the capacity of dynamic RAMs has increased as the size of our transistors gets smaller and smaller and smaller, but the latencies in the dynamic memories, which are pretty much controlled by the size of the memory, have have not increased dramatically. These are a little better than the first DRAMs that came out, but not by several orders of magnitude, or 3 or 4 orders of magnitude that we've gotten for processor speeds. So this is a problem. We need to go solve this. And so we're going to sneak up on the answer today. First, I'm going to tell you a little bit about each of these different types of memory technologies, so you at least get a glimpse of what they look like. And then we'll set out to seeing if we can solve this puzzle about how do we make a fast processor that has to access a slow memory. So keep that in your mind as what our goal is today. Okay, so first up on the list is the sort of technology that we're using inside of our register file, a so-called static RAM. And at the heart of the static RAM, I hope you recognize that diagram. It's a little bistable loop made by a little loop of inverters. And that loop will reliably remember a value. So if I have a 0 on one side, I'll have a 1 on the other side of this little loop, the other side being the other of the 2 nodes. And this little loop, as long as I keep it plugged in, well, even if there's a little bit of noise and one of these voltages gets slightly corrupted, it'll be restored by the logic gates. And it's quite happy. And you can see here that to read the information out of the loop, what we're going to do is to, I've got some information stored in this cell. In fact, I've stored a 1 bit in this cell. So one of these 2 nodes is a 1, and the opposite, the 1 on the other side of the inverter is a 0. And the way I read information from this cell is I'm going to put a 1 on the word line, the line that will turn on these access field effect transistors, and basically couple this bit line here to the information that's stored in that particular cell. If I wanted to read out a different cell, I would be turning on a different word line. And the reason it's called a word line is that this structure here is replicated horizontally, in our case by 32 times, because we're going to read out 32 bits in parallel to read out an entire word. So this word line actually end up going to 64 different access FETs. So when I assert a particular word line, I'll get 32 bits out the bottom. And then what happens is once I turn on these access FETs, these very small these FETs are made out of these inverters are made out of reasonably small FETs, and to keep the size of the SRAM small. And so what I've done is I have this line that in our case will connect to 32 different bits in a column. And so I have some capacitance here to drive because of the capacitance associated with the drain of the access FETs. And so as these small transistors are busily trying to charge and discharge this line. So this is a little slow. Being not nearly as fast as a logic gate. So there's this sort of an analog circuitry going on here. And in fact, what I do is I build a fancy analog circuit called a sense amp that listens to both bit bar and bit, looks for a small difference between those 2 values because they're going in opposite directions. And as soon as that difference is a small number of millivolts, I don't have to wait for them to get to be legitimate logic values. I'm not building a digital circuit, I'm building an analog circuit that's sort of trying to deduce digital values from small changes in voltages. And so I get my answer out reasonably quickly, but because it's an analog circuit. Even more analog-y is this idea that I'm going to write simply by putting a very strong driver, something that has huge FETs in it, that can supply a lot of current, and I'm basically going to punch this little feedback loop in the nose. I'm going to turn on the FETs and say, you're now a 1, and this little inverter is saying, no, I'm pulling it up, I'm pulling it down, it's a 0. And I'm going, no, 1. and what happened, and the volume of my voice is meant to represent the amount of current that's being supplied to that node, and I can actually flip the value of that cell by writing a strong 1 and a strong 0 here. And so this is very analog. You're saying, what happened to this dynamic, the static discipline? And you're saying, we're not living in that world anymore. Okay, so, and these cells, it takes 6 transistors for each one, and then there's a sense amp circuitry and all that. So it's a clever bit of engineering that gets the job done. They're hard to design. I mean, they're not something that ordinary mortals should do. You have to be a fairly clever analog designer with some years of experience to get these to work reliably, depending on what the manufacturing line is doing and the temperatures and the power supplies and things like that. We can build a multi-port SRAM simply by having multiple bit lines and selecting and multiple word lines that will basically allow us for each of the different read ports to select the output of a different cell onto the line. And there's some little details here about rearranging the circuit slightly so that the capacitance of the bit lines doesn't end up flipping the cell accidentally if we tried to read it out into too many of the read ports at the same time. Now, a dynamic RAM, which is the high-capacity memory system that you guys buy when you buy your laptops or your home machines, or you use one of the machines in the cluster, is much simpler. It involves a single field effect transistor, which is the access FET, and the storage is accomplished by simply putting charge on a capacitor. Right, and there's a lot of work to make those capacitors, have as much capacitance as possible, but in as small an area as possible, so that because I want the much capacitance in order to have the value that I'm trying to remember last a long time. So there are all these little leakage currents going on, and the bigger the capacitor, the longer it will take before that value leaks off. I would like, however, for the cell to be as small as possible so I can fit billions and billions and billions of them onto the little chip I want to build. And so you start getting very strange looking structures. I don't know how well you can see this in the slide. This sort of looks like a rotten tooth, right? And what it really is this is a cylinder where there's an internal metal cylinder that's been covered by a dielectric insulator, and then there's another plate of the cylinder, that's another metal plate that's gone on top of that. So I've made this cute little dielectric metal sandwich, which is basically a very small capacitor. Nowadays, memories are built with trenches. Same idea. You build a deep trench into the silicon wafer. You line the inside of the trench with metal, and then a layer of insulator, then another layer of metal to build these capacitors. These capacitors aren't very big. They do leak as time goes on. And so what happens is that I have to come back. The reason they're called dynamic is that once every 10 milliseconds or so, I have to come back, read the information off the capacitor, and rewrite it. Otherwise, I'll lose the information that's there. So every 10 milliseconds, circuitry in your computer is basically reading out every location in your main memory system and writing it back in again. So it's like the old Chinese, a circus act where you see the guys spin the plates, and they start spinning plates, and he's got 40 plates going, and then all of a sudden the one at that end is starting to wobble, and he runs back to spin that one a little faster and keep all the plates balanced. Well, that's what your dynamic memory system is doing for you behind the scenes. This is an inherently slow process. There's not much charge here, so it actually takes a fair amount of time to read a piece of information out of this cell. And the circuit itself involves these word lines are quite long. There's billions of these little cells in one of your memory chips. So this piece of circuitry is actually not as fast as one would hope. So to increase its throughput, we're going to pipeline it. You know how to do pipelining. And so, in fact, what we do is we send over the address often in a couple different groups. Now, we don't send in one clock cycle, we don't send all the address to the memory. We send about half of the address, and the next cycle we send the second half of the address because we don't really need it here as quickly as one might think we do. And the whole process of decoding the address and selecting the word lines and reading the information out of the memory cells, and then selecting which ones to send back to which one of these. We're often reading, in this case, hundreds and hundreds of bits in parallel, and then selecting the 32-bit quantity we want to send back. So this is a so-called synchronous dynamic memory. Synchronous because it's basically pipelined. And the so-called DDR RAMs that you all have in your machines use a clock transmission protocol where on both edges of the clock we're sending information. So this is really the bottleneck. The reason your machine is as slow as it is because getting information to and from the memory system is pretty much what's limiting the performance factor. So even with all this engineering of a pipeline system and using both edges of the clock to transmit data, this is sort of going to limit us. Okay. The trouble with this memory system actually has reasonably high throughput. It can sort of keep up with the consumption of the processor in terms of instructions, but sadly, it has a long latency. Once I have an address here, getting the first address, the first piece of data out of the memory is slow. After that, I get words, every couple of nanoseconds. But getting that first word out can take quite a while as it gets processed through the pipeline. Yes?
I might be mistaken, but it seems that not all paths here go to the same amount of data.
Well, I think the goal is for them to actually do that. What happens is that the address gets decoded, right? So there's sort of, if you sort of follow an address through, right? If there's a bug in the ARCs, I apologize. But yeah, clearly for all the usual reasons, we need a well-formed pipeline here. I'll look more at that diagram to see if I can find your bug. Okay. The hard disk drive is the high-capacity memory in your system. We can get, hundreds of gigabytes and terabytes. It's a spinning magnetic medium. In other words, we're actually reading and changing the orientation of these little, magnetic domains that are part of the oxide that's on the surface of the disk. We can get a huge amount of information on not very much disk these days. We have clever ways of sort of recording it like in sort of concentric circles. And when you basically read a disk, you're telling it where it should position the head, which concentric circle you want to read from, and then which sector of that circle actually holds the bits that you want. And so you actually are sending over a sector number, and that spews out of the disk. Modern disks actually read the whole track at a time, buffer it in a little local buffer memory, and then when you say, I want a particular sector of a track, it will basically say, oh, okay, I actually have that whole track, so I'll just dump out of my little local fast memory, my little local SRAM. I'll go ahead and give you the little piece that you want. But if you change tracks, then you have to wait for this disk to spin. It's spinning, 7,500 or 15,000 RPM. So it takes, a millisecond or a fraction of a millisecond to get the disk to spin around, and then mechanically moving the head in and out also takes something on the order of milliseconds. So disks are high capacity but very slow. Okay, so that's sort of a brief tour of the memory technologies that are available to us as engineers. Now what we're going to do is say, well, what is it we want, right? We have a choice of these capacities, these technologies at this end, which are very inexpensive, and we can afford to buy, billions and trillions of bytes of information. But we want our computers to run very fast, and so it seems like we're going to be stuck having to spend lots and lots of money on the fast memories. And so what we really want, if we could somehow arrange it, is the best of both worlds. Okay? We want a very big memory that's also very fast. And we can almost get our wish, surprisingly enough. And what we're going to do is spend some time working on the technology that will make our wish come true. And as you can imagine, the scheme we're going to use is going to use sort of a hybrid, which is a combination of these small but very fast memories and large but very slow memories. And what we're going to hope to do is to get something that is both big and fast. And statistically, that will turn out to be true. And so we're going to sort of rely on some statistical arguments about the sort of, what addresses we ask for in which order. And by looking at the statistics of memory accesses, we're going to be able to engineer a system that, on the average, does very well. In the worst case, it suffers from the big memories being slow. But on the average, our system will perform quite well. So let's sort of explore that for a bit. So the key idea, which I'll say now and we'll look at in a graphic representation in the next slide, is that when you think about how a computer operates, it mostly is not asking for addresses willy-nilly. For instance, think about how the program counter is going through memory, right, as we're fetching instructions. Mostly it fetches instructions one after another. And occasionally there's a branch, maybe often back to an instruction, back to the beginning of a loop, so back 10 instructions or so. But there's a certain orderliness to the access patterns. And in fact, there's what we call locality of reference. If I look at the amount of the references that are made by the computer over some span of time, if I reduce that span of time to a small region of time, on the order of tens or hundreds of instructions, I'll discover that the number of memory locations that I'm trying to access is actually very modest. In other words, I tend to ask for, if I'm asking for memory location at location X, in the next cycle I'm very likely to be asking for the one at location X plus 4, particularly if it's instructions. And because of looping and behavior of our programs, if I've asked for an instruction in the past, chances are, there's some probability, a reasonably good probability, that I'll ask for it again in the not too distant future. So we're going to take advantage of that. So let's look at some possible memory reference patterns, and this is sort of a very schematic diagram of trying to sort of plot memory references versus time. So if I think about a program, a program that has loops and subroutine calls and things like that, I might expect to see a reference pattern that looks like this, where the addresses sort of increase as I execute instructions sequentially. I might jump back to the beginning of the loop and execute that loop several times. Occasionally I might branch forward in my program, an if statement, something like that, and skip over a couple of instructions. I might make a subroutine call and go off and to some entirely new region of memory. So that sort of represents a discontinuity in my nice orderly sequence of addresses. But once I'm past that discontinuity and I'm in the body of the subroutine, it becomes orderly again. Okay. Occasionally it gets higgledy-piggledy. Particularly if you're doing, method dispatches on objects in an object-oriented programming language. But by and large, this is not just random access. There's some orderliness to the accesses. That holds even more true of the stack. And almost invariably, we're accessing the local stack frame. As we do procedure calls and stuff, the stack frame grows, where we stack rows, and we might access a new stack frame. But in general, we're accessing a very small region of the stack at any given moment, the activation record for the current procedure. And in terms of data accesses, we're accessing structs in memory, or perhaps stepping through an array. In some cases, as shown here, we may in fact be copying from one array to another. So we might have a couple, a load and a store, where the load comes from one data structure and the store goes into another data structure. But it's not like we're, that most programs have a certain systematic way in which they're dealing with particular objects at a particular time, or dealing with a particular part of the array at a particular point in the program. And so if you put all this together, you can see that in a particular span of time, the actual number of dots, the range of addresses that appear here in the blue region is actually limited. There's a limited number of program locations and a limited number of stack locations and a limited number of data locations that I'm accessing. So that's what we mean by locality of reference. Okay, and in fact, if we make that blue region wider and wider and wider, and say, well, if things are not well behaved, the wider we make it, the more locations we would expect to be accessed. But in fact, for most programs, you'll discover that the number of locations that are accessed, for any given width of that blue region, for any given sort of little span of time, at some point, it dramatically drops off. In other words, even though I could double this blue region, at some point I won't double the number of memory locations that I'm accessing because of looping, and I keep using the same data structures, and I keep referencing the same stack frame. So even though I'm considering a longer span of time, I'm still working with the same old memory locations. And that is going to be the key to our engineering trick. Okay. Okay, so we're going to exploit the memory hierarchy, and we're going to have this notion of, well, we have a small fast thing and a medium-sized memory and then a very slow but very large memory off on the hard disk. And we're going to use this hierarchy. So what's the trick? What's the trick? If I'm accessing a certain set of locations a lot, where should those locations live? In the fast memory. And everybody else can go live in slow memory, and only when I access them the first time, what am I going to do? I'm going to move them into the fast memory so I can get to them there. And eventually the fast memory gets full, and what should I do then?
Get rid of the oldest stuff?
Get rid of something. What should I get rid of? When you open your refrigerator back at the dorm, and you go, oh my God, and you say, well, I got to put stuff in the new keg of beer, what do you throw away? Yeah, the old keg of beer. What you have to do is you sort of you have a replacement strategy. You pick something that you probably say, if I throw it away, I won't miss it very much.
Sentient leftovers.
Yes, sentient leftovers. I like that idea. Okay, so that's the basic scheme, right? We're going to try to put the things we want to access into the small fast memories. Now, there's two basic strategies we could pursue. I'm still thinking about sentient leftovers. The two basic strategies I could pursue. One is I could, this is the thing hardware types love to do. SMOP. Everybody know what SMOP means? S-M-O-P. A small matter of programming. Right, and so us hardware types who are lazy basically say, oh, the program guys, they'll figure it out. So what I'll do is I'll just build this hierarchy, right, and I'll just tell you to put, it'd be up to you to, if you want your program to run faster, you should devote some instructions to moving the things you want into fast memory. It's up to you to figure it out. You'll know better than me. Right? And that was the approach that was advocated by Seymour Cray when he built his fancy vector machines, which for many decades were the fastest machines on Earth. He basically had these very fast pieces of memory that would hold the vectors, and it was up to the programmer to figure out how to load the vector registers and then how to use them. And his famous sort of speech about this was, look, you don't have a large fast memory, you have a small fast memory, and you can't fake what you haven't got. Okay, well, Seymour was very clever, and in fact, quite remarkably, over the span of several decades, his machines they held the speed record. They were always the fastest machines on Earth. So this was a man who sort of knew what he was talking about when it came to circuit design and computer architecture. However, this is one occasion where I think Seymour was wrong. Okay, as it turns out, we can fake what we haven't got, and that's because we're behaving rationally. It is possible for us to build hardware that will automatically manage where a particular memory location can be found. Okay, where you don't have to think about it. So you just access memory like you normally would, using addresses that your program generates. And the hardware will sort of look over your shoulder and say, I see what you're doing. You're starting to read from the foo routine. Maybe I'll get the rest of the instructions of the foo subroutine into fast memory, into a fast program memory. And when you ask me for them, I'll already have them. How clever. Right? So the machine could take advantage of the fact that there's some systematic patterns to our accesses and then do a good job of doing this automatic memory management. And what I want to spend the rest of this lecture and the next lecture doing is we're going to look at the details of how that hardware works and why it works. Okay, it's sort of fun, actually. It's sort of neat to imagine that we can actually, solve this riddle, that we can get something where our machine really does work at 1 billion instructions per second. It actually needs a new instruction every nanosecond. Okay, yet our main memory system isn't capable of producing a new instruction, randomly, anywhere near that fast. Somehow it all comes together and works. So we want to understand that hardware. Okay, so if we ask for a particular memory location X, the hardware will actually first look in its little cache. That's going to be our name for this small fast memory. And it will see is that address something that I've already sort of thought you'd asked for and I have in memory, or that you previously asked for but not very long ago, so I haven't taken it out of the refrigerator yet. It's not sentient. So Sorry. So you look at this and you say, okay, first I look in my cache. If I don't have it there, then I'm going to have to go look in the main memory. And in fact, in most modern systems, when you start a program, it doesn't bother to read the program off of your disk storage and put it into dynamic RAM. It just leaves it on the disk, and only the first time you access it, it gets so-called paged into main memory, and then from main memory into the cache. So there's this sort of a combination of hardware and software that is going to automatically manage getting your program and your data, your instructions and your data, into the storage level of the storage hierarchy where they should be at any given moment. And by and large, if we do this well, mostly when we ask for an address, more than 95 or 96% of the time, we'll be able to find that information in that static cache. Any questions about the basic plan? Now you can say to yourself, well, I see a big CPU and the small yellow box labeled cache. The reality of the situation is the proportions are a little different. If you opened up the Intel chip that you have and looked at where it put its transistor budget, most of the several billion transistors that you've bought are actually in the yellow box. Okay, most of what you buy is cache memory. So the size of the cache is important, and the faster you want your computer to run faster, it's not so much you have to make the CPU faster, you have to make sure that on the average you're finding more and more and more information in the yellow box. And the way we do that is by making the yellow box be able to hold more and more bits. So the real key to performance in most systems in the modern world is large amounts of cache. And in fact, in the sort of memory, the computer chips that you have, there's actually 3 levels of hierarchy of the yellow boxes. Okay, so there's increasingly larger but slightly, but a factor of 2 smaller cache systems, and there's a stack of those even before you get to the main memory. So this hierarchy idea really works, and we've done a lot of engineering in the modern chips to sort of deliver it to you in the most tasteful form. For our purposes, we're going to imagine a single layer of yellow box. Okay, so the cache idea. How does this work? Well, of course, 100% of the time, the CPU is asking, certainly every cycle, for an instruction. And then we're going to look in the cache. And what we mean by look is, I'll describe that hardware in a moment. And alpha percent of the time, this is called the hit ratio, we hit in the cache, meaning the address that we're looking for is in fact the contents of that address are already in that yellow box. Okay, so and the rest of the time is not there, and we have to go off and look in dynamic memory. And in fact, we can, using the access time of the cache, which tends to be on the order of an instruction, the same sort of speed as the processor is executing instructions. Okay. And the access time for main memory, T sub m, which is often several orders of magnitude slower. What we want to do is to figure out what sort of hit rates do we need to get in order to get an average access time that's much closer to TC, the fast number, than it is to TM. Okay, so that's one goal, is to figure out what sort of hit rates we need and then wonder if we can build hardware that will get that hit ratio. The second goal, so we get a good average access time. And the second goal is to make sure that we don't, the programmer doesn't really have to bother their head about this, right? Because it would be awkward to have you think, not only you have to get the functionality right, but then you have to spend a lot of time worrying about, where in the memory hierarchy things are. So that's our goal. It's been somewhat defeated in recent years by the existence of multiprocessors, which have this problem in spades. If we have trouble keeping one processor fed with information from memory, imagine if you have 4 cores or 8 cores. and we have to keep them all fed from there. We have 8 hungry children all going, chirp, chirp, I'm hungry, where's the worm? And say, look, I can only get worms so quickly here. And so, in fact, in the modern world, if you want to build high-performance, multi-core applications, you starting to have to be more aware of the memory hierarchy than maybe we would like. Okay. So how high of a hit ratio do we need? Well, suppose we have a 4 nanosecond cache memory and a 40 nanosecond main memory. If we want an average access time of 5, in other words, only slightly slower in the cache, you can see that we actually need a very high hit rate. Over 97 some odd % of the time, when you ask for a location, the hardware has to say, oh, I've already got that. So keep that number in mind, and we're going to work on figuring out how to make that happen. The good news is that, remember that diagram where I showed the working set size, the number of locations sort of over a span of time, how it sort of went, there was a knee in that curve? The good news is that if we can sort of, so here's, there's the size of that working set, okay, as I made the delta t interval bigger, okay, sort of it flattened out. The good news is if I can build a cache that's big enough and that I can get all of these locations in the cache, I should expect a reasonably high hit rate, because that's all over a big span of time, those are the only locations I'll need that the CPU will be asking about. So you experience this a lot, right? When you first type Python, when you power on your machine and type Python, you can look there and you're sort of drumming your fingers and you're sort of going, this is taking a while, right? You Control C, you type Python again, and you get the prompt right away, right? So there's a lot of things that are happening when you first start up a program where things are being moved into faster locations of the memory hierarchy that the next time you use it, it turns out it's there, and everything is orders of magnitudes faster. Okay, so let's talk about this cache principle. And what I've done, so here's a little sort of a virtual thought experiment. So we have file cabinets, which are slow, and I've invited Clark Kent to join us today, Superman, to serve as our high-speed memory. And so it takes 5 minutes to look in the file folders, but only 5 seconds for Clark to say, okay, I have the information that you want. So I'm in the next room yelling addresses outside of my office door, and there's somebody out. So Clark is out there along with the file cabinets, and I say, "Bit diddle Ben, I want information." That's the address that I'm sending. And the algorithm is, well, Clark's going to quickly look to see if he happens to be holding what I need. In other words, is it in the cache? And if so, he can respond quickly. Okay. The difficulty, but then he has to go off to the file cabinet. And I'm hoping that we can come up with a scheme that when I'm yelling names out of my door, that mostly Clark will answer rather than the file cabinets. So that's what I want. And what I'm going to do for a few minutes is to sort of use this little thought experiment to explore the things that can go wrong with the scheme and see if we can figure out how to fix them. And then we'll look at some hardware. So the basic algorithm is the CPU will produce an address, and we'll have this cache, which we're representing here as a table. And the table contains both information about which addresses are stored in the cache, and then the actual memory contents of those addresses. So the cache knows two things. It knows which addresses it has, and it has the contents of those addresses. That makes sort of sense? And so the CPU, when I ask for a particular address, will look through the cache, will search the cache, and we'll talk about how that's done in just a second, to see if I ask for memory address A, oh, it says I've got that, and it will respond. If I'm writing to memory location A, it will say, fine, I have that in my cache. You're telling me a new value for it, so I'll just update the cache. And the processor can continue on, and then the cache itself will worry about updating main memory with that new value. If there's a miss, what does it mean to miss? I ask for C, address C, and it's not in this table. Hopefully that doesn't happen very often, but when it does happen, I have to go off and pick some line of the cache, that thing in the refrigerator I'm going to throw away, the sentient thing apparently, The thing in the refrigerator I'm going to throw away, and I'm going to then replace it with the contents of memory location C. So the first time I ask for C, I have to go off and fetch it from memory. That's okay. I mean, it's the only choice I have. It's slow, and the CPU is drumming its fingers, saying, I'm still waiting for C. It doesn't have much to do. I'll talk more about that next time, actually. The whole notion of hyper-threading is Intel's answer to what happens if the CPU doesn't have much to do. Maybe it could go work on some other program while it's waiting, for some number of cycles for the main memory to get back with the answer to your cache miss. Okay, so I have to pick a replacement and go off to the main memory and bring it in, and I'm going to put it in the cache in the hopes that you'll ask for it again. And statistically, we hope that will be true, and that's how I hope that, in fact, the hit rate will be reasonably high. Okay, and if we believe this diagram about locality of reference, the answer is once I get all the elements of my working set into the cache, you will keep asking about them again and again and again. The same parts of the stack frame, the same instructions from memory. And so once I put it into the cache, having made an investment to put it there, then I'll take advantage of it being there again and again. So how do we search the cache? Well, the most obvious thing to do is to actually have an office full of Clark Kents outside my office door, each of whom has a piece of paper, in the hopes that somewhere in that stack of information, I'm going to do this sort of parallel search. Right, so what I'm going to do is to ask all of this team out here to say, okay, find me bit diddle, and they're each going to look at their piece of paper in parallel, right, and sort of go, aha, I've got it, and the other guy's saying, no, not me, not me, but one guy has it. Alrighty, so this notion of sort of the best type of search we can do is to look at every row of my cache, every line of my cache, to see it, and I'm asking for a particular address, to see if that particular cache line has the address, and I'll look at all the lines in parallel. So I'm going to design a piece of hardware where I'm going to use these registers here to hold both the data itself and something we call a tag. What's the tag in our cache? What information do we need in order to find a piece of data? We need its address. Right? So I call a tag here, because that's the sort of jargon name that we give the indexing field of a cache. And we know that to mean the memory address. The CPU is asking for an incoming address, so each of these tag fields holds an address, and the associated data register is holding the contents of the memory location that has that address. So I'm going to build hardware comparator, using XOR gates and OR gates and AND gates to basically compare each bit of the address with the corresponding bit in the tag, and if they all match, I'm going to say, I've got it. And one of these lines will respond, and if it does, I get a hit back to the processor, and I put the appropriate data onto the lines. Everybody happy with that? So a fully associative cache. Look at the ratio of the hardware to the actual data storage, right? So we have a register holding the various data words, but we have to hold that big address, which is as big as the data in the case of a beta. We have this comparator circuit. We have all this routing circuitry we have to put in. These are very expensive. Right? These fully associative caches are very expensive. We will find occasions to use them, but in terms of, they're very, very good. If we have it in the cache at all, we'll be able to find it quickly just in the cost of this small piece of combinational logic to do the comparison. So in orders of picoseconds, I'll be able to say, I've got it, but I have to spend a lot of hardware to get there. So is it expensive? Is there a cheaper alternative? Well, suppose I only could afford to have one clerk sitting outside my office, okay, but I want him to be able to respond quickly to a bunch of different questions. Well, suppose he kept a whole stack of papers, not all the papers, they're in the file cabinets, but a small subset of the papers organized. He can store one paper for each first letter of the last name. Right, so when I ask for a bit diddle, he's going to look in his little B slot, which he can do quickly. Right, he just reaches over B slot, looks at it and says, aha, is this page filed under B happen to be bit diddle? So this notion of what we call a direct map cache, where we take some of the information that's coming in, we take the address, that in this case the name, and we have a mapping function that tells us which, and we have a small array in our, we're going to look in our cache, and each of the incoming addresses will be found in a specific slot in the array. And which slot it is depends on how I map the addresses to the slot number. But once I've done that mapping, I will look in that slot and happen to see if I have that address. Right, so I'm coming up with sort of a way in which I can sort of organize my cache memory. It's going to be relatively inexpensive because I'm only going to be doing one comparison. And I'm going to be using some information from the incoming address to pick which one of the small number of slots to look at. Okay, now the problem with this scheme is that depending on how I map the incoming address into the slot, I may potentially have a lot of requests, all of which map to the same slot, and then my cache isn't doing me any good. I keep asking for Bs, and there's only one B slot. Right? So I have to be a little careful in choosing how I map the incoming address to slots to make sure that most of the addresses that are coming in sequentially, and remember there's sort of a pattern to these addresses that are coming in. Okay, I want to look at that pattern, understand what that pattern is, and try to figure out a mapping function so that most of those addresses will map to different slots. And then I can get away with a single comparison. Okay, and in this particular case, if I sort of organize by last letter, okay, in this sort of trivial thought experiment, you can see I do better because they're mapping to different slots. So, and it doesn't eliminate contention, but we hope that statistically we might be able to do well if our mapping function is likely to map elements of our working set to different locations in the cache. That's really what we want to do. These are the locations we're trying to access, this set of locations. Okay. If I can get them to all live in different locations in the cache, hopefully without having to buy a fully associative cache to do it, I should be in good shape. And it turns out, and this is where we're going to spend some time getting to, it turns out we can come up with a hardware architecture that does this. So here's sort of the circuit diagram for a direct map cache. We're actually going to use one of these small fast memories, okay, a memory system that has, at most a few thousand locations. So to make it fast, we're going to use the low order bits of the address as an index to pick the slot we're going to look in. And then we're going to compare the high order bits of the incoming address with the tag field to see if we have that information. So any particular address, any particular combination of bits, will, if it lives in the cache, will live in a very particular line of the cache. Okay, and that line is determined by the low order bits of the address. And then to check to see if that line is holding the information we want, we compare the high order bits of the address, the ones that weren't part of the index into our cache memory. So these high order T bits, we compare them against the tag field in memory. So this, as I say, this memory here is built out of these small but fast caches. The little top level caches that you have, the level 1 caches you have, are probably only a few thousand entries long. Okay, but they're very quick. They respond in tens of picoseconds. So, and there's a single comparator associated with each one of these pieces of cache. So that's a direct map cache. We haven't completely solved the contention problem. The idea of using the low order address bits is good because, in theory, if we're doing mostly sequential accesses, because we're stepping through a program or something like that, the low order bits or the higher order bits stay the same as the low order bits that are busily incrementing, right? As you go 0, 4, 8, C, all those zeros at the top still stay 0 as the low order bits that are changing as I walk through the different addresses of a program. And occasionally I go back to the beginning of the loop. If I can arrange for all the instructions in the loop to map to different cache lines, then I will find all the locations of my loop in the cache. And this particular, using the low order address bits, okay, as the index here, is my key for mapping the address to my limited number of cache slots in a way that I expect that to win most of the time. Everybody sort of see the reasoning there, why I'm expecting this to work okay? Okay, now we always have contention. In other words, it is possible if I do a data access or I jump to a different part of my memory that I'm going to produce some low order bits that overlap the ones that corresponded to the program I was running, and now the information won't be in the cache. So I do have this contention problem. There will be some misses, and our goal for next time, okay, next Tuesday, is to see here my direct map cache was attractive because it was inexpensive but suffered from a collision problem. This cache can always store any set of n addresses. Okay, there's no notion of a collision because any address can live anywhere in the cache. I don't have the problem of two different addresses mapping to the same cache location, and then I can only be storing one of them, so the other one's a miss. The fully associative cache is very attractive from a notion of collisions because it doesn't have any, okay, but it's very expensive in hardware. So our next step is to see, is there a happy middle ground? And there must be, because your machines work pretty well, and we'll discover that next Tuesday. Anyway, good luck on finishing Lab 4, and we'll see you in section tomorrow and in lecture next Tuesday.